This video covers sections 22.1 through 22.5, and this is the beginning of the chapter on amines. Amines are classified as primary, secondary, tertiary, or quaternary, and you should know this by now that primary has 1 R group, secondary has 2 R groups, tertiary has 3, and then quaternary has 4 groups. These can be alkyl groups, or you can have, for example, one of the substituents could be a hydrogen atom, and it's quaternary because it has 4 substituents. To name amines, you list the names of the groups that are attached to the nitrogen in alphabetical order, and then you add the term amine. So I want you to pause your video and see if you can name the following amines. The first one is is propylamine. The second one is diphenylamine. Then we have triethylamine. And lastly, with our substituents, ethyl, propyl, and butyl, we need to arrange them in alphabetical order. So this is going to be butyl, ethyl, propyl, amine. I'm going to talk a little bit about the properties of amines. The boiling point of amines is midway between an alkane and an alcohol. For our alkane propane, we have minus 42 degrees C as our boiling point, and with ethylamine, we have 17 degrees C, and with ethanol, we have 78 degrees C. Lots of the low molecular weight compounds smell fishy. They can be pretty gross. This one is called cadaverine, and this longer molecule is called spermine, and they smell like their names. pKa's vary based on the substituents and the state of charge. Can you think of the one that is the least acidic, and also which one is the most acidic? Pause your video and see if you can find the most acidic and least acidic. The most acidic compound is this one with a pKa of 0.5. 4. And you might ask yourself, why is this the most acidic proton? Most acidic molecule? And that's because when this molecule loses a proton, it becomes aromatic. So there's a driving force for it to lose its proton. The least acidic compound is the neutral amine that has a pKa of around 38. In between that, we have a protonated propylamine with a pKa of 10.5. We have a protonated form of diethylamine with a pKa of 11. And then our pyridinium cation has a pKa of 5.3. This slide is a reminder of the preparation of amines. This is what you already know. In the first example, we're going to take sodium cyanide to turn our alkyl bromide into an alkyl cyanide. And notice here that we're adding a carbon atom. So we're going from 3 carbons to 4. Then in our next step, we're adding excess lithium aluminum hydride followed by water to reduce that nitrile into an amine. Then with the carboxylic acid, we can use SOCl2. Charlie Brown. And that forms the acid chloride. And then in the next step, excess ammonia is used to turn this into an amide. In the next step, we use lithium aluminum hydride to reduce that amide to the primary amine. Our third reaction involves the nitration of benzene followed by reduction with either hydrogen on palladium or iron with acid followed by sodium hydroxide. And our last reaction involves a derivative with nitro substituent and an aldehyde. And here you can use tin chloride and acid, and that is followed by sodium hydroxide to give you an amino compound. Next, we're going to talk about preparation of amines via substitution reactions. The first is alkylation of ammonia. And here we see that if we combine ammonia with iodomethane, then we get methylamine. And if we add more methyl iodide, then we get dimethylamine. If we add even more, then we get trimethylamine. And if we add even more, then we get our quaternary amine, which would be some sort of salt. And because we're using iodine as our compound with the leaving group, this would be the I- salt. Our next reaction involves azide synthesis, followed by a reduction reaction. Here we have sodium azide reacting with an alkyl halide to form an alkyl azide. Then we follow that with reduction with hydrogen on palladium, or we use lithium aluminum hydride to reduce this compound to the amine form. Let's look at the mechanism for how this second set of reactions, lithium aluminum hydride, works. So first we're going to install the azide, replacing bromine as a good leaving group, and that gives us the azide compound. This is reduced and we expel nitrogen gas. So nitrogen is a really stable compound, and that makes it a good leaving group. In our next step, we have the deprotonated form of our amine, so we need to have water in step 2 so that we can make the neutral amine compound. Our next reaction is the Gabriel synthesis, and this is a way to make primary amines. This reaction involves 3 steps. First, we have potassium hydroxide to deprotonate our amine, or our nitrogen hydrogen. Then this is followed by an alkyl halide, which puts an alkyl group on the nitrogen atom, and this is followed by acidic water, which means that you get a hydrolysis reaction to form this bis-carboxylic acid and the primary amine. How does this work? Let's look at an example with bromopropane. First we have our deprotonation reaction, then we have an SN2 reaction to connect to that propyl group. And then our next step is hydrolysis, and that's a really long mechanism, and you've seen it before, so I'm not going to go through that. But if you need a refresher on this mechanism, go to mechanism 20.6 in section 20.10 of your book. If you use hydrazine, then you can get a faster reaction. Here we've already started with an alkyl group attached to the nitrogen, so that means we've already gone through the step where we've installed the alkyl group using potassium hydroxide and our alkyl halide. We then use hydrazine to form this compound and our primary amine. So this is a reaction that is used because it is faster than hydrolysis, which is a pretty slow reaction. Next, I want you to do a practice example where you make this amine in a Gabriel synthesis. So pause your video and see if you can come up with the synthesis of this compound. So in any Gabriel synthesis, we're starting with this thiol-imide compound, and we need to deprotonate it. Then we need to look at what's attached to the amine group and install it. So everything that is highlighted here needs to be added to our amine, and it's got to come from an alkyl bromide. Okay, on the next slide we have another practice. So pause your video and see if you can draw the alkyl halide and the carboxylic acid that could be used to prepare this compound, and show your reagents too. So let's start with the alkyl halide. We need to be in a position where we're going to add a carbon atom to the alkyl halide. So we want to add this by treating the compound with sodium cyanide. Always make sure that your bonds to triple bonds, that these are planar, or these are, they're linear bonds. So don't draw them bent. Then you know from chapter 20 that an excess of lithium aluminum hydride followed by the addition of water is going to give you the amine. In the example with our carboxylic acid, let's work backwards. And see how we could have gotten there. So here I'm going to use lithium aluminum hydride followed by water, because I know I want to have a carbonyl in this compound. And specifically, the precursor should be an amide. Then when we think about how do we get to amides, well, we get to amides from using I was a step off there. We get to amides by treating acid chlorides with ammonia. And then to get to the acid chloride from a carboxylic acid, we want to use SOCl2. So this is the carboxylic acid that we need to start with. That is all for this video. Have a good day.